So last time we were working on this problem. This like pseudo leg thing. There's a pin joint there connecting these two members. I called this 1 and 2. And the joints A, B, C. That's 45. That's a right angle. And omega 1 was equal to omega 2 equal to negative 10 radians per second. And we had an external couple of positive 100 Newton meters on member 1 and negative 100 Newton meters on member 2. And we had a length of 0.5 for each of these and a mass of 5. Okay, and we came up with a system of equations. I don't think, did I give you the final answers? Okay, so we, the last thing we worked on was coming up with this constraint equations. The system of equations looks like, well, let me just put it into matrix form. Okay, so we had 6 equations and 6 variables. So there's equation 1, 2, 3, 4, 5, 6. And for variables, I'll go f12x, f12y, a2x, a2y, and those are the components of the acceleration of the center of mass of member 2, and then alpha 1 and alpha 2. And so equation 1, the first 2 equations are Newton's second law for member 1. We get negative 0.3535 for f12x. Positive 0.3535 for f12y. For alpha 1, we get negative 0.4167. And for the constant, we get negative 91.33, threes forever. And then the y, Newton's second law equation. Oh, no. No. That first equation comes from the rotational Newton's second law for member 1. Because we have a fixed point, so we're not using Newton's second law. So now equation 2 and 3 are Newton's second law for member 2. f12x is negative 1, a2x negative 5, and then all the rest are zeros. Equation 3, f12y is negative 1, a2y is negative 5, and the constant is positive 49.05. And then the rotational equation for member 2, f12y is negative 1. Nope, that's the one I just did, sorry. f12x is negative 0.1767. f12y is negative 0.1767. Alpha 2 is negative 0.104, and the constant is 100. And then equations 5 and 6 are the 2 constraint equations, saying that the 2 members have to agree about the acceleration of the pin joint that connects them. A2x is negative 1. Alpha 1 is negative 0.3535. Alpha 2 is negative 0.1767. And the constant is 17.67. And then equation 6, A2y is negative 1. Alpha 1 is positive 0.3535. Alpha 2 is negative 0.1767. And the constant is negative 17.67. And I don't have the answers here. I know I had them somewhere, but does anybody have answers from yesterday? And if not, will a few people plug these in so we can hopefully get the same answer? So we're going to get F12 A2, the acceleration of the center of mass of 2, and then alpha 1 and alpha 2. Okay.
18.66. 58.89.
Okay.
6.92.
Okay.
Negative 219.42.
Anybody else get something like that?
Yep.
Okay, great. Okay, and so we're almost done with this problem. We're done with the hard part, but we haven't answered the question yet. The question was, what's the acceleration of that point C? Okay, so the way we're going to do that, well, how do you want to do that? I'll tell you if your idea is stupid or not. Yeah, relative motion in the watermelon equation. Yeah, so the acceleration of C relative to the ground is equal to the acceleration of C relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. And this one is what we've been calling A2, so we have values for that. The acceleration of the point C relative to the center of mass of 2 comes from the watermelon equation. So we have alpha 2, 0, 0, negative 219.42. Crossed with the r vector. What's the r vector? Well, to describe it, since we're doing our rotation about the center of mass, that's what it says, that we're doing it relative to the center of mass. We want an r vector that goes from the center of mass to our point of interest. So what would that be? That would be negative
0.7071
times, and that distance is a quarter. So 0.1, I think that's negative 0.1767, right?
Yeah.
And then positive 0.1767, 0. And now the omega part. So what's omega for member 2? that's, yeah, they're both negative 10 in the z direction. So 0, 0, negative 10, cross quantity, 0, 0, negative 10, cross with that same r vector again. And could someone calculate that? Okay. Okay, so then finally, the acceleration of c relative to the ground is 56.44, 21.10, plus what we got for A2, so 18.66, 58.89. And what do you get for that? Okay. Meters per second squared. Any questions about that? All right, so now we're going on to the wackiest topic in this class, the most confusing one. And that is particle kinematics and kinetics. In rotating coordinate systems. Okay, so yeah, this is going to get a little harder to visualize and stuff. So remember, first of all, that the laws of physics only apply in inertial coordinate systems. And there are two ways a coordinate system can be non-inertial. The first one is that the origin is accelerating. And the second one is that the axes are changing orientations. So, in other words, the coordinate system is rotating. This one we've dealt with a bunch in this class already, and in Physics 1 you dealt with it, some too. This one, all we have to do to take, so if we know the way that the origin of our coordinate system is accelerating, and we're given measurements in this accelerating coordinate system, we can deal with that just with relative motion. So we know how to do that. This one, though, we haven't done yet. And of course, you could, and a lot of times you do have, you're taking your measurements in a coordinate system that's rotating and the axis is, and the origin is accelerating, and you just have to do both of these two steps, Okay, so what goes wrong? What changes when the coordinate system axes change orientations over time? Well, first, think of how you take a time derivative. So remember, our gateway from kinematic quantities into kinetic quantities are Newton's laws, right? They have to do with velocities and accelerations. And those velocities and accelerations are time derivatives of positions, right? So time derivatives are really important things to us. So first, think about what happens when you take the time derivative of a vector. So take d dt of a vector u. This is just some arbitrary vector in your coordinate system in a non-rotating coordinate system. Well, u dot is just equal to d dt of ux, uy, uz, right? And so that's equal to ux dot, uy dot, uz dot, which is equal to ux dot times I plus uy dot times j plus uz dot times k. But if I, j, and k are changing in time, and that's what's happening. You see why that's what's going on if your coordinate axes are changing orientation. Then the time derivative of u is d dt of, so here's the vector u, and the product rule says take that time derivative and you get ux dot times I plus ux times I dot plus uy dot j plus uy j dot plus uz, this should be a j dot, plus uz dot times k plus uz times k dot. And if you rearrange these, what you get is ux dot times I plus uy dot times j plus uz dot times k. Okay. And this, notice, is the way you would take a derivative in a non-rotating coordinate system. But then you also have this added piece that's equal to ux times I dot plus uy times j dot plus uz times k dot. And this is the piece that causes all the headaches. So notice that you could think of this, do the product rule to calculate the time derivative in a non-rotating coordinate system. But this second set of terms here, these all go away because there's no change in I over time. So I dot is equal to 0, no change, you know what I mean? Okay, so so how does that work? Let's think sort of intuitively about what's going on. And let's do it by thinking about one of those astronaut training things. So let's say that we have a camera at the center of a rotating axis. And this camera defines our coordinate system. So let's say, there's a coordinate system attached to this camera. And at the end of this arm is one of those high G-force. They put the astronaut in one of these chairs and spin it around at a high speed. And so this astronaut's going in a circular path like that. Okay, so let's say that this has a length of 5 meters. And let's think about, okay, so, and imagine put sensors in the chair to measure the force. Measures the force that the chair applies to the astronaut. And what I'm going to do is draw a sketch of what that camera sees as the astronaut goes by this point in 2 cases. So the camera measures the astronaut's motion 2 ways. The first way is that camera is fixed there, and so the orientation of the camera is fixed, and the astronaut only appears to that camera every time he goes around. You know what I mean? So the camera doesn't rotate. And so it only sees the astronaut once per rotation. Is that, so the camera, the coordinate system attached to that camera, is that an inertial or a non-inertial coordinate system? That's inertial. That camera is fixed in space, and it's measuring the astronaut's motion as the astronaut goes by. So we should have no problem using the laws of physics in this coordinate system. The second way it's going to do it is the camera rotates with the astronaut. And so it sees the astronaut the whole time. This is a non-inertial coordinate system because the axes of this coordinate system are rotating. Okay? So I want to just do a little demonstration, thought experiment demonstration of why these two coordinate systems are not going to agree about the acceleration, and why the non-inertial coordinate system is going to give us false information if we try to use it in Newton's laws. Okay, so the first way, so the camera doesn't rotate. So here's frame 1. This is like a film strip. Frame 2 and frame 3. So what does the camera see in frame 2? Let's say that's the instant that the astronaut goes right into the camera's view. Okay? So an instant before that, the astronaut's there. An instant after that, the astronaut's there. These are 3 different positions. And you can use that to measure speed, centripetal acceleration, etc. Okay. Then, so you get a non-zero acceleration. The chair measures a non-zero force. And it turns out that Newton's second law holds there. So let's think about what happens in the rotating coordinate system. So there's the film strip. At instant 2, again, the astronaut's right in the middle. what does the camera see the instant before that? The same thing, because the camera is moving around, just staying right on the astronaut. And so at instant 1, they see that. At instant 2, they see that. At instant 3, they see that. So according to this coordinate system, there's no motion and no acceleration. And so you get an acceleration vector that's equal to 0. The chair still measures a non-zero force. So Newton's second law doesn't hold. Okay. So you need to intuitively, just thinking about it this way, if you're using calculations that come from a rotating coordinate system, you need some kind of correction term. So you need a correction term to use Newton's second law with accelerations from a rotating coordinate system. And what are those correction terms? Well, the acceleration that you're measuring from the rotating coordinate system is just equal to px double dot, py double dot, pz double dot. That's what you're measuring there. The correction term comes from the a better way to think of it is just think of the acceleration being the velocity dot, okay? When you measure this acceleration equal to 0, what you're measuring is vx dot, vy dot, vz dot. The correction term you need to add is this, this, and this. Okay. So that's what we're going to do. Any questions about that? That's sort of a philosophical introduction to it. But we'll talk about how to calculate that correction term. Okay.